The locally weighted regression is a method that combines idea from both regression and local analysis. Unlike traditional regression, the locally weighted regression is a technique which attempt to fit a single global model to the entire data set. Locally weighted regression focuses on fitting the model only to a small region nearer to the query point. Let us imagine you are trying to predict a value based on nearby data, much like how you might predict the weather for tomorrow by considering today's condition in your area, rather than relying on a global weather model. This method is called local because it only considers data points that are nearer to the point of interest, and weighted because it gives more importance to closer data points. Okay, now consider locally weighted regression in which the target function f is approximated near x cube using a linear function of the given form. This is a linear function which is used to find the approximation for a target function f, where ai of x denotes the value of the ith attribute of the instance x. So, on the training data example, uh, if we want to minimize a squared error, we use some uh, gradient descent rule. This is a gradient descent formula in the perceptron, which gives the gradient descent rule as dw of j equal to eta of summation of x belongs to d of f of x minus f cap of x into aj of x. This is a gradient descent rule which is used in perceptron, which is used to find out the error, and a weighted vector which is used to minimize the error, where uh, eta or nu is a constant learning rate. So, in order to minimize the error, there are three possible criterias. First one is minimize the squared error over just the k nearest neighbor. On just the k nearest neighbor, if you want to minimize the squared error, we can use the following formula. This is the following formula which is used to minimize the error on just the kth nearest neighbor. Suppose if we want to minimize the error over an entire training example, while weighting the error of each training example by some decreasing function k of its distance from x cube. This is the formula which is used to minimize the squared error over entire set of training examples. Now let us move on to the another criteria in order to minimize the error. Now let us combine the equation 1 and 2, we'll get the third equation. If we choose criterion 3 and rederive the gradient descent rule, we obtain the following training rule. This is a new gradient descent rule which is used to minimize the error. The difference between this rule and the rule given by the equation 3 are that the contribution of instance x to the weight update is now multiplied by the distance penalty, and that the error is assumed over only the k nearest training examples. Okay, now let's move forward on radial basis functions for function approximation. Why we use the radial basis functions? Okay, the radial basis functions are used for function approximation and are closely related to distance weighted regression and artificial neural networks. The radial basis functions are mainly related to distance weighted regressions and artificial neural networks. Okay, the main purpose is to approximate a target function by combining radial basis functions. We use radial basis functions mainly for approximating a target function. Okay, now the key concept of radial basis function is in this the hypothesis is represented by using the formula, and this is the formula which is used to represent the hypothesis in the radial basis function, where the xu is the instance from the x, and where the kernel function, the ku of d of xu comma x, is a kernel function, is defined so that the kernel function decreases as the distance d of xu comma x increases. Here k is a user provided constant that specifies the number of kernel functions to be included. And the f cap is a global approximation to f of x. F cap is a approximated functions of f of x. The contribution from each of the ku of d of xu comma x terms is localized to a region nearby the point xu. So consider a working example. Imagine a scenario where suppose you want to approximate a function that predict house prices based on features like size and location. So how you can use the radial basis function in order to approximate the function which predict the house prices. So in this, the kernel function is the use Gaussian kernels centered at training instances. For example, house sizes and location with variances. Now, to combine these kernels to form a smooth approximation of the house price function. Now, let us move on another topic, case-based reasoning. Now, let us see what is case-based reasoning. The case-based reasoning is a learning paradigm that classifies new instances by analyzing and adapting solutions from similar past cases. It classifies in new instances based on the solutions from similar past cases which are stored in the memory. And it uses a symbolic representation of cases rather than real valued points, focusing on similarity to solve new problems. Okay. The key concept of case-based learning is it classifies new queries based on the closest matches in a stored case library. That is, suppose a new instance query is occurred. It classifies that query based on the searching the closest match which is stored in the library. It searches the closest match. Based on that, it classifies new queries. So it represents cases are represented with rich descriptions that capture structural and functional details. It uses symbolic representation in order to represent the case and new queries. Now, consider a working example of case-based learning. Here, consider a system, CADET system for designing mechanical devices. So, this system has already contains 75 previous designs and design fragments. These are the design data which is already stored in the case library. So, in this, each case is described by its structure and qualitative function. So, suppose a new instance query is occurred, that is a specify desired function and a requested design based on similar past cases. So, how it classify a new case is that first of all is check the most similar past cases which are present in the case library. Based on that, it classify the new query. Suppose the new query is a faucet with specific temperature control. Then it will search the case library, then find the most similar case and classify the new query. So, in conclusion, the instance-based learning methods are powerful tools that adapt to the specific cases rather than generalizing across all the data. This works for the specific cases only. The techniques like k-nearest neighbor, locally weighted regression, and radial basis functions and case-based reasoning allows for flexible and accurate modeling, making them invaluable in real-world applications where precisions and adaptability are key. So, in the real world, if you want to predict something, it it requires a precision. We need to predict a specific value. So, in real world, the instance-based learning are invaluable. These are used for prediction of high accuracy. So, these are the concepts which have been covered. So, hope you have enjoyed the learning.